Alexander Graham Bell first reported photoacoustics over 100 years ago. He had this concept of photophone instead of telephone. His idea was to encode a sound signal into a light beam, then propagate the light beam in space, convert light back into sound again through the photoacoustic effect. So what happens in the photoacoustic effect is light is first absorbed, it generates a temperature rise. Due to thermoelastic expansion, you generate sound emission. Now, Bell was interested in the audible frequency range. We're interested in the ultrasound frequency range, so we can shorten the wavelength of the sound for better spatial resolution. We can define the structures better and see the tumors better. Photoacoustic tomography has a very simple analogy. The principle is extremely straightforward. It's like triangulation. Imagine there's a thunderbolt. When you see the lightning, you can reset your stopwatch. When you hear the thunder, you can record a time delay. Multiply the time delay by the speed of sound in air, you can define a radius for a spherical shell on which lightning took place. If you have 3 such concurrent measurements, you have 3 such spherical shells, the intersection of the spherical shells will pinpoint the thunderbolt. Except in photoacoustic tomography of a complex 3D object, we have to have more than 3 measurements in order to figure out the 3D distribution of many photoacoustic point sources. So in order to achieve tomography or 3-dimensional images, we expand our laser beam in most cases. We allow photons to wander around, but any absorbed photons will be useful. They'll contribute to photoacoustic signals. For every millidegree temperature rise, we generate hundreds of pascals pressure rise because, again, the sound propagation is so well defined in tissue, we can collect the ultrasound emission signals. From there, we do math to reconstruct the image. There are a number of applications. We can start from the very superficial cases like melanoma. Or we can miniaturize the device for the GI tract, the gastrointestinal tract, or colon. This device can be very useful for breast cancer imaging, maybe prostate cancer imaging, brain imaging. We're also thinking about breast cancer staging using this device, early prediction of response to chemotherapy, detection of circulating melanoma cells, tumor cells, maybe even dosimetry control in thermal therapy. We've adapted a commercial ultrasound imaging machine for concurrent photoacoustic tomography. The hope is that physicians will adapt our technologies more easily because they're comfortable with ultrasound imaging. Now, by turning on a switch, they can see the photoacoustic contrast as well. So this combined technology will give them much more information.